Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome, everyone. Today we are doing a deep dive into, well, one of the biggest mysteries out there about our own planet's history. It's a real cold case.
It really is.
We're talking about the moment Earth, fundamentally started to breathe, the event that really set the stage for all complex life for us.
The Great Oxidation Event, the GOE. And the scale of this change it's hard to overstate, really. Billions of years where Earth was basically an oxygen-free zone, a reducing world.
Holding its breath, as you put it.
Yeah, exactly. Then, somewhere around 2.1 to 2.4 billion years ago, things flipped dramatically. Suddenly, there's this massive release of oxygen into the atmosphere.
Changing everything forever.
Absolutely. But here's the kicker, the big puzzle scientists have wrestled with.
Right.
The microbes responsible, these tiny little things called cyanobacteria. They figured out how to make oxygen way before the GOE actually happened.
Hundreds of millions of years earlier, right? That's the baffling part.
Could be 300, maybe even 500 million years. Think about that gap. It's enormous. You've got the oxygen factories, they're built, they're running, technically capable of pumping out oxygen.
But the atmosphere isn't changing. The lights are off, globally speaking. So the question's always been, why? Why the huge delay?
Yeah, if the generators were online, what was stopping the grid from powering up? There have been theories, of course.
Good ones.
Like volcanic gases just sucking up all the oxygen. Or other microbes eating it.
Exactly. Those are definitely part of the picture. But they never quite seem to fully explain that incredibly long, stable delay and then the sudden shift. It felt like something was missing.
A bottleneck somewhere.
A bottleneck, yeah. And that's where this new research comes in. It's work out of Okayama University, led by Dr. Dylan Ratnayak, published recently. They took a different angle. Instead of just the big planetary sinks, they looked smaller.
Exactly. They zoomed right in on the microscopic level, the ecological factors. What was actually controlling the growth of the cyanobacteria themselves? Could they thrive, or were they just sort of sputtering along?
Okay, so finding the precise control knob at the microbial level.
That's the idea. And their research points to two, maybe surprisingly simple compounds. Nickel and urea.
Nickel and urea. Okay, that's not what usually comes to mind with planet scale changes.
Right. But this study suggests they were the keys. First, locking the oxygen supply down, and then eventually unlocking it.
So that's our mission for this deep dive. We're going to unpack exactly how nickel and urea could have acted as this biogeochemical bottleneck. We want to give you that aha moment, connecting the dots between tiny microbes and the whole planet's atmosphere.
Let's get into it.
Okay, so let's set the stage properly. Section 1, the Great Oxidation Delay. We need to appreciate just how big a deal the GOE was.
It's truly a fundamental turning point. Before the GOE, you've got what's called a reducing atmosphere. Think lots of compounds that readily react with oxygen-reduced iron, sulfur, methane. Things like that dominated.
So any free oxygen that popped up would just get instantly consumed by the surrounding chemistry?
Pretty much, yeah. The environment had a huge capacity to soak it up. And when oxygen did start to build up significantly, it was actually, toxic. A crisis for much of the life that existed back then, which was anaerobic, didn't use oxygen.
Right. Oxygen was poisonous to early life. It's ironic.
It is. But it was this very crisis, this environmental shift, that ultimately paved the way for, us, for complex, multicellular life that needs oxygen. This transition marks the boundary between the Archean and Proterozoic eons, roughly 2.4 billion years ago.
And the agents of this change, the little heroes or villains, depending on your perspective back then, were the cyanobacteria.
These incredible microbes, they perform oxygenic photosynthesis. Basically, they take sunlight, water, CO2 stuff that's everywhere, and turn it into energy for themselves.
And oxygen is the waste product.
Oxygen is the exhaust, exactly. A revolutionary invention.
But an invention that, based on genetic evidence, seems to predate the GOE by a massive margin.
Yeah, the molecular clock studies looking at the genes of modern cyanobacteria and tracing them back strongly suggest the evolution of this process happened maybe 300, maybe 500 million years before the atmosphere actually registered it. The tech was there, the impact wasn't.
So let's revisit those earlier theories for the delay. You mentioned the big sinks.
Right. Traditionally, the thinking focused on these massive planetary buffers. One was geological volcanic activity. Early Earth was much more volcanically active, pumping out loads of producing gases: hydrogen, sulfur dioxide, methane.
Gases that just react instantly with O2.
Instantly. So it's like a giant geological vacuum cleaner constantly running, sucking up any oxygen the cyanobacteria managed to produce. That kept levels incredibly low.
Okay, that makes sense. What was the other main idea?
The other focused more on chemical sinks within the oceans themselves, and maybe other microbes. The oceans were full of dissolved iron, for example, which rusts, oxidizes very readily.
So the oceans themselves were acting like a giant rust bucket, consuming oxygen.
Effectively, yeah. Plus, maybe other early microbes, non-oxygen-producing ones, were super efficient at gobbling up any organic matter or trace oxygen that appeared. A biological sink working alongside the chemical one.
So you had this planetary tug-of-war, cyanobacteria producing oxygen on one side.
And volcanoes, ocean chemistry, and maybe other microbes consuming it on the other side.
And the argument was that these forces were just perfectly balanced for 500 million years. That seems improbable.
That's the tricky part, isn't it? Maintaining such a perfect, delicate balance for such an incredibly long time, and then having it suddenly fail.
Yeah.
It always felt a bit, well, unsatisfying. Plausible, sure, those factors were important, but maybe not the whole story.
It didn't explain why the producers, the cyanobacteria, didn't just eventually overwhelm the sinks earlier.
Exactly. The older models focused heavily on oxygen consumption. They didn't look as closely at factors that might have been limiting oxygen production in the first place by suppressing the cyanobacteria themselves.
Which is where the Okayama study pivots. They're looking at these cyanobacteria's diet, essentially, their immediate chemical environment.
That's the core idea, looking for ecological constraints. Dr. Ratnak's team focused on trace elements and simple organic compounds, things that might be present in small amounts but could have huge regulatory effects on life.
And they zeroed in on nickel and urea. Why those two?
They had a hunch, based on biochemistry, that these two might have this interconnected, really crucial role in limiting cyanobacterial growth, specifically back in the Archean eon. They suspected an ecological control mechanism was the real bottleneck, something that didn't need a new evolution to overcome, just a change in the environment to release the brakes.
Finding that microscopic switch in a giant planetary system. I'm hooked. All right, let's dive into the evidence itself. Section 2. How they actually tested this. This wasn't just computer modeling, right? They did lab experiments.
Oh yeah, really rigorous experimental work. It had to be done in two parts, really. First, they needed to establish that their key players, nickel and urea, were actually plausible components of the early Archean Ocean, around, say, 4 to 2.5 billion years ago, before the GOE kicked off.
Makes sense. You can't have them be the bottleneck if they weren't even there.
Precisely. So, experiment part 1 was all about abiotic urea formation. The question was, could urea, which we know is a vital nitrogen source for life, actually form without life making it, through purely chemical processes?
Abiotic meaning non-biological origin.
Exactly. And they needed to simulate the conditions of early Earth, which were pretty brutal.
How so?
Well, the big thing is the lack of an ozone layer back then. Earth's early atmosphere didn't have much oxygen, so no ozone shield like we have today. That meant intense, high-energy ultraviolet radiation, specifically UVC, was just blasting the surface, including the oceans.
And UVC is pretty nasty stuff, right? We use it for sterilization.
We do. It's highly energetic, breaks down molecules, but that energy can also drive chemical reactions that wouldn't normally happen. So simulating that UVC exposure was crucial for accurately mimicking the prebiotic environment. If a reaction needed UVC, it might have happened then, but not now.
Okay, so intense UV light. What ingredients did they put in their simulated primordial soup?
They used a mix of simple stuff thought to be common back then, things like ammonium, cyanide, and dissolved iron compounds, basic building blocks readily available from volcanic outgassing or hydrothermal vents.
And they zapped this mixture with UVC light.
Yep. They exposed these mixtures to UVC radiation and then analyzed the results to see if urea CONH2 had formed.
And did it?
It did. They confirmed that urea could indeed form abiotically under these plausible early Earth conditions.
Why is that single finding so important for their overall argument?
It's foundational. Because if urea could only be made by complex biological processes, then its availability in the Archean Ocean might have been really limited or patchy. Maybe that was the bottleneck, just not enough nitrogen in a usable form.
But if it forms abiotically,
then it was likely just there, a constant background component in the ancient oceans, produced by sunlight hitting common chemicals. It wasn't a rare nutrient that life had to invent ways to make. It was an environmental factor life had to deal with, for better or worse.
Okay, so urea was likely present. Step 1 confirmed. What was step 2? Experiment part 2.
Right. Now they needed to see how varying levels of this urea, along with nickel, actually affected the growth of the oxygen producers themselves. So, testing cyanobacterial growth.
And they needed a stand-in for ancient cyanobacteria.
Yeah, they used a well-studied, robust species called Cyanococcus sp. PCC 7002. It's a modern cyanobacterium, but it's often used as a model organism because it grows relatively quickly, and its basic photosynthetic machinery is thought to be representative of those early forms.
Makes sense. So how did they set up the growth tests? What were they controlling?
It was all about careful control.
Hmm.
They grew the Cyanococcus under standard conditions, things like controlled light-dark cycles to mimic day and night. But the key manipulation was the growth medium, the soup the cyanobacteria lived in.
They tweaked the recipe.
Exactly. They created different batches with systematically varied concentrations of urea and nickel. Some batches had low urea, some high. Some had low nickel, some high. And importantly, they tested various combinations: high urea, low nickel, low urea, high nickel, high, high, low, low. All the possibilities reflecting potential archean conditions.
Covering all the bases. And how did they track if the microbes were actually growing well or not? How do you measure that?
They used standard microbiology techniques. 2 key metrics. First, they measure the optical density of the liquid culture, basically how cloudy it gets. As the cyanobacteria cells multiply, the culture becomes more turbid, blocking more light passing through it. More cloudiness equals more biomass.
Okay, a measure of overall growth.
Yep. And second, they measure the concentration of chlorophyll. That's the main pigment cyanobacteria use for photosynthesis. So tracking chlorophyll gives you a direct measure of the photosynthetic capacity of the culture, how much oxygen-making machinery is present.
Got it. 2 different ways to measure success. And what did they find? Was it just more urea, more growth?
Not at all. It was much more complex. It wasn't a simple case of urea being just food. They found this intricate relationship, this dual role, where the combination of nickel and urea concentrations was the critical factor.
Dr. Ratnaya called it complex yet fascinating, right?
That's the quote. The key finding wasn't about the absolute amount of urea, but the ratio of nickel to urea. That ratio seemed to dictate whether the cyanobacteria could actually flourish or if their growth was actively suppressed, even if there was plenty of nitrogen theoretically available in the form of urea.
So it wasn't simple starvation. It was something more like interference.
Exactly.
Yes.
Pointing towards more subtle chemical control mechanism rather than just basic nutrient limitation.
Okay, this is where it gets really interesting. Section 3, unpacking the biogeochemical bottleneck model itself. How did high nickel and urea actually work together to suppress life and delay the GOE?
Right, this is the core of their proposed mechanism. To understand the bottleneck, you need to picture the Archean ocean chemistry. The model suggests that back then, concentrations of both nickel and urea were significantly higher than they are today. And crucially, it was this combination of high levels that acted as the suppressor.
Okay, hang on. I'm still slightly stuck on why high urea would be bad. We established it's a nitrogen source, and nitrogen is essential, right, for proteins, DNA, everything.
It is essential, absolutely.
And nickel, isn't that also a trace nutrient needed for some enzymes? So why would having more of these essential things be bad? It feels counterintuitive.
It does seem paradoxical, but the devil's in the biochemical details. It comes down to a specific enzyme called urease.
Urease, okay, what does that do?
Cyanobacteria, like many organisms, can't use urea directly as is. They need to break it down first into simpler, more biologically available forms of nitrogen, like ammonia. Urease is the enzyme that does this job. It catalyzes the breakdown of urea.
Okay, so urease is the tool they use to process the urea food.
Exactly. And here's the crucial link to nickel. The urease enzyme absolutely requires a tiny amount of nickel to function. Nickel acts as a cofactor, fitting into the enzyme's active site and helping it do its chemical work.
So they do need nickel.
They do, but only in trace amounts. Here's the problem. The Archean oceans were apparently swimming in nickel compared to today.
Why so much nickel back then?
It's linked to the Earth's geology at the time. There was much higher geothermal activity, lots of deep-sea hydrothermal vents spewing out dissolved metals, and also a specific type of magnesium-rich volcanic rock called comatite was much more common then. These rocks are very rich in nickel, and as they weathered or interacted with seawater, they released a lot of nickel.
So nickel concentrations were way higher.
Potentially orders of magnitude higher, maybe 400 times the concentration we see in modern oceans based on geological evidence, way, way above trace nutrient levels.
Okay, so too much of a good thing. What happens when the urease enzyme encounters these super high nickel levels along with high urea?
That's where the inhibition comes in. When nickel concentrations get that high, it stops being just a helpful cofactor and starts coming up the works. The excess nickel ions essentially compete for or interfere with the active site of the urease enzyme.
They block it.
They interfere, yeah.
Mm-hmm.
Especially when the enzyme is already trying to bind and process lots of urea molecules because the urea concentration is also high. It's like the enzyme gets overwhelmed and effectively poisoned or jammed by the sheer abundance of nickel ions hitting it while it's trying to work on the urea.
Wow. So the cyanobacteria are floating in this ocean full of potential nitrogen fuel, urea. But the tool they need to use that fuel, urease, is constantly being sabotaged by the massive overdose of nickel.
That's the bottleneck mechanism in a nutshell. They're effectively starving for usable nitrogen right in the middle of the urea feast because their metabolic machinery to access it is chemically inhibited by the nickel overload.
So they can't grow efficiently. They can't divide rapidly and form massive blooms.
Exactly. Their proliferation is suppressed. You might get small, localized, short-lived blooms, perhaps, but not the sustained planet-wide explosion of cyanobacteria needed to overwhelm the oxygen sinks and fundamentally change the atmosphere. The nickel-urea combination acted like a powerful brake on the whole system.
That explains the lights-off period, the Great Delay. The factory was built, the fuel, urea was there, but a key piece of machinery, urease, was jammed by nickel.
Okay, so what released the brake? What caused the tipping point for the GOE?
According to this model, the trigger wasn't some new biological invention or mutation in the cyanobacteria. It was a gradual, large-scale change in Earth's geochemistry that naturally lowered the nickel concentration in the oceans.
The planet itself changed the conditions. How? Why would nickel levels drop?
This links back to major geological shifts happening around that time, roughly 2.5 billion years ago. The Earth's mantle was slowly cooling down.
Less internal heat.
Less internal heat, which meant overall volcanic activity likely decreased somewhat. Crucially, the formation of those super nickel-rich comatite rocks largely ceased. The source of excessive nickel started to dwindle.
Okay, less input from volcanoes. And at the same time, large, stable, continental landmasses cretins were forming and growing. The emergence of continents changed global weathering patterns. More land surface means different types of chemical weathering, potentially locking up nickel and minerals on land rather than letting it wash into the sea.
So less nickel coming in from volcanic sources and maybe more getting trapped on land or in sediments. The overall supply dropped.
Exactly. The input decreased, the sinks might have changed, and gradually, over millions of years, the concentration of dissolved nickel in the oceans fell. It dropped from those incredibly high inhibitory Archean levels down to something much closer to the trace nutrient levels we see today.
It crossed a threshold, below the level where it poisoned the urease enzyme.
That's the critical idea. Once nickel dropped below that toxic threshold, the urease enzyme was finally free to work efficiently again. Cyanobacteria could now effectively utilize the urea that was still present.
The metabolic brake was released.
The brake was off. With non-inhibitory nickel levels, cyanobacteria could access the nitrogen they needed, and they began to proliferate massively, globally, sustained large-scale growth.
And that sustained, massive growth finally produced oxygen faster than the geological and chemical sinks could keep up.
That is the Great Oxidation Event, triggered by the geologically driven decline in oceanic nickel.
Wow. That really reframes the whole story. It wasn't about waiting for life to figure out oxygen production. It was about waiting for the planet's chemistry to allow the oxygen producers to truly take over.
It puts the timing squarely in the court of planetary geochemistry controlling microbial ecology. The moderation of nickel, and by extension the effective usability of urea, paved the way for the oxygenated world.
A much clearer, more mechanistic explanation for that huge delay. This is fascinating just for understanding Earth history, but you mentioned earlier this has implications beyond our own planet. Let's get into that in Section 4, the so what for searching for life elsewhere.
Absolutely. This is where the research really connects to astrobiology. Dr. Radniak explicitly points this out. If we want to find life on other planets, understanding the mechanisms that allowed life here to fundamentally reshape its environment is critical.
It's not just about finding life, but finding life that's had a planetary impact.
Or understanding why it hasn't, even if it exists. We often assume that if life evolves, it will inevitably boom and change its planet, maybe producing biosignatures like oxygen that we can detect. But this study is a powerful reminder that life can exist for vast periods while being ecologically suppressed, stuck.
So when Dr. Ratnaik says this sheds light on biosignature detection, it's not just about looking for oxygen.
It's about looking for oxygen in context, or perhaps explaining its absence. Imagine we find an exoplanet that looks potentially habitable with the right temperature, maybe signs of water. We analyze its atmosphere. Maybe we don't see much oxygen.
We might assume life isn't there or isn't photosynthetic.
Right. But this research gives us another possibility. Maybe life is there. Maybe it even invented oxygenic photosynthesis, but it's stuck in its own great oxidation delay because of a chemical bottleneck. Maybe its star system or planetary geology keeps baiting the planet in high levels of nickel or some other inhibitory trace element.
So we need to consider the planet's geochemistry, its likely trace element environment, alongside the atmospheric gases.
Exactly. The star's composition can give clues about the elements likely abundant in its planets. The planet's age and inferred geological activity matter. It adds a whole new layer to interpreting potential biosignatures. We shouldn't just look for the smoke, oxygen, but also for the damp wood, the chemical inhibitors that might be preventing the fire from starting.
And this has direct relevance for missions we're planning now, like Mars sample return.
Very direct. The paper mentions this provides a new framework for the sample analysis strategies. When those precious Martian rock and soil samples eventually get back to Earth labs.
We'll be hunting for fossils, organic molecules.
Yes, but we also need to be meticulously analyzing the trace element chemistry of those ancient Martian environments. If we find sediments from a time when Mars might have had liquid water, maybe even signs of ancient microbial mats or textures, we absolutely need to measure the nickel concentration in those same layers and look for evidence of nitrogen compounds like urea or its precursors.
Because if we find signs of past life, but also evidence of super high nickel levels from that same era,
it could provide a powerful explanation for why Martian life, if it ever arose, might never have reached the scale needed to oxygenate the planet like Earth life did. It might have been stuck in its own biogeochemical bottleneck.
It shifts the question from just, was there life, to, were the conditions right for life to thrive and reshape the planet?
Precisely. It's a more nuanced, ecologically informed approach to the search.
And broadening out beyond Mars to exoplanets orbiting distant stars.
Right.
We can't get rock samples there, obviously.
Not yet, anyway. But we can analyze the light passing through their atmospheres, looking for chemical fingerprints.
So the interplay between inorganic stuff like nickel and organic stuff like urea was key on Earth. We should expect similar complex chemical controls on other worlds?
It seems highly likely. Biology doesn't happen in a vacuum. It's constantly interacting with its chemical environment. Different star systems will have different elemental abundances. Different planets will have different geological histories, different levels of volcanism, different atmospheric compositions. It's almost certain that other bottleneck elements or compounds exist out there, controlling the fate of potential biospheres.
So the big lesson for alien hunters is, don't just look for the oxygen.
Or rather, understand that oxygen's presence or absence might depend heavily on these subtle chemical constraints. Look for the conditions that allow oxygen-producing life to dominate. Is the environment chemically permissive? Or is there some trace element, like nickel was on early Earth, acting as a planetary handbrake?
It really adds layers of complexity, but also makes the search potentially more revealing, thinking about these chemical governors.
Yeah, it tells us that planetary habitability isn't just about having the right temperature and water. It's also about having the right trace chemistry. Too much of even a necessary nutrient can stall life's ability to transform a world for billions of years.
Incredible that for maybe 500 million years, the entire trajectory of complex life on Earth hinged on the concentration of nickel jamming up one specific enzyme.
It really puts things in perspective, doesn't it? The intricate dance between geology and biology. So let's wrap this up. We've covered a lot of ground, from 20 microbes to planetary atmospheres.
We have. And the core takeaway from this deep dive from the Okayama University research is pretty revolutionary, I think. That huge, baffling delay in the Great Oxidation Event wasn't primarily about waiting for evolution to invent something new.
Right. The machinery, the cyanobacteria capable of making oxygen, was likely there for a long, long time. The delay was fundamentally about chemistry and ecology.
Specifically, the high levels of nickel in the Archean oceans, acting in concert with high levels of urea. The nickel effectively poisoned a key enzyme, urease,
preventing the cyanobacteria from efficiently using the available nitrogen, which suppressed their growth on a massive scale. It created a powerful biogeochemical bottleneck.
And the planet only started breathing, kicking off the GOE, when long-term geological changes, cooling mantle, changing volcanism, continent formation, caused the nickel concentration in the oceans to drop below that critical inhibitory threshold.
Releasing the brake, allowing cyanobacteria to finally bloom globally and pump out enough oxygen to permanently change the atmosphere.
And the ripple effects go way beyond Earth history. This gives us a whole new framework for looking for life elsewhere.
Definitely. It tells us to look beyond just the presence of potential biosignatures like oxygen and consider the enabling or inhibiting chemical context. Are there trace elements acting as bottlenecks on other worlds? It adds crucial nuance to how we interpret data from Mars or distant exoplanets.
It makes this incredibly complex billion-year story suddenly click into place, connecting microscopic enzymes to the fate of the entire planet. Hopefully you, the listener, feel like you've got that aha moment now, understanding the nuts and bolts of this ancient bottleneck.
So we'll leave you with a final thought to mull over, building on this idea. If a chemical bottleneck, high nickel levels, held back Earth's oxygenation for maybe 500 million years, what subtle chemical factor, what unseen trace element might be playing a similar role right now on an exoplanet that otherwise looks perfectly ripe for life?
Could there be countless worlds out there teeming with microbial life, just patiently waiting for their own planet's nickel concentration or something equivalent to finally drop so they can kick off their own Great Oxidation Event?
Makes you wonder what the universe might look like in another billion years, doesn't it?